right, thank you guys for hopping on. We'll go ahead and get started. Today we will be doing risk management and system mission assurance. Dr. Lee Jasper is going to be presenting for us today. So we'll just pass it on to him to go ahead and get started.
Okay, so real quick, I went to the University of Colorado and I'm an old UNP alum as well. I worked on Nanosat 5 and 8, Dandy and Polar Cube respectively. But I've been working on CubeSat stuff for quite a while and on sounding rockets and things like that. I got my PhD at CU. I was looking at debris removal, which is still a hot topic, but it was definitely big then because we had the Chinese ASAT test and some collisions and stuff about that time. So a lot of interesting research was happening at that point. But overall, since then, I worked at JPL for a few years on a really big synthetic aperture radar mission. That's a partnership with the Indians, and that was a lot of fun. That has yet to launch, but that is a huge Earth science mission. So we'll get a lot of cool data out of that eventually. Yeah, and I blow up a small town out in Kansas every year called Selden. But yeah, I do a fireworks show, which is, oh boy, a lot of things I have learned from UNP and other places. So yeah, it's a bit about me. You haven't heard my voice. You probably will at some point throughout this cycle, as I do a lot of reviewing for UNP as well. All right, cool. Enough of that boring stuff. So, all right, we're talking about mission assurance and risk assessment. And so I wanted to ask a broad question and actually maybe have a little bit of discussion here. So anybody online, I guess, how would you guys describe mission assurance, or do you even know what it is? All right, anyway, so what is mission assurance? Everybody's not totally sure. That's what we'll go with. Oh, I do have one chat. All right, cool. Vincent said, making sure everything goes to plan. That's mission assurance. Yeah, to some extent, that's about right. There are a number of definitions for how you would do this, but making sure everything goes to plan, or really, as I was trying to state it colloquially, like activities that help you improve the chances of mission success, right? That's really what we care about, is getting the mission done, making sure everything goes right. That's exactly it. A bunch of people think and talk about this in different ways. And so there's a bunch of different definitions. I kind of like the second one, aerospace corporations. The disciplined application of proven scientific, engineering, quality, and program management principles toward the goal of achieving mission success. Right, so there's science engineering behind the practices that we do for mission assurance. So this is not a thing you necessarily learn in school a whole lot, but it certainly is a thing that is used pervasively throughout the industry. Where does mission assurance occur? Basically, it's spread across all levels of what we do in the project, right? As the aerospace thing said, it was science, engineering, quality, program management, right? Like that kind of covers the whole gamut of what you may be doing on a mission. From an engineering perspective, there are activities that you do at the systems level, and that can span all the way down to like individual piece part component selection, like resistors, capacitors, what have you. Mission assurance literally can cover that whole thing. But a lot of what is spent time-wise is actually in the communication piece. And those are things like risk management, which we'll talk about more shortly, but even like design reviews or more detailed like failure review boards or things like that. Reviews are really kind of a part of mission assurance. Failure reports, capturing lessons learned, all those types of things can kind of be in that larger bin of making sure that the mission is actually successful. And just a note, right, many organizations, as you go out and graduate, you'll see that they have an independent group that might be doing mission assurance. And the idea behind that is you want someone to be looking sort of without all the pressures of a project to make sure like the right things are happening and the right activities are being performed such that we're not compromising the mission at the expense of meeting a timeline, or even saying like, I know what I'm doing, I don't need anyone to check me. Mission assurance ideally is to help with a little bit of those types of things. So the next few charts, I'm going to kind of give the top level overview of how we do mission assurance. And there are two fundamental approaches to doing this. The traditional one is what is well known throughout all of the industry as class A through D. This was created a while ago, back in 1986, by the Department of Defense for, as they say, one-of-a-kind space equipment. NASA and the Department of Defense use it pervasively. The Europeans and Japanese and Indians don't have the same system, but there's a lot of commonality between what they do and what we do. So this is very much a United States system, but it's not. You can kind of know what other guys are doing in other countries based upon this system. So the basic flow and process for how do you do Class A through D is define the class and then follow the guidelines for that. And there are pretty well-defined guidelines. At the very top level, I grabbed this out of a NASA document. Class A through D, they sort of categorize them based upon the priority or significance of our mission. How complex is it? How costly is it? Based upon how those things are ranked, you can see that, you might be a Class B or a Class D or something. These are fairly subjective metrics, right? There's no hard and fast rule for what the cost is or what we mean by complexity. You can kind of see a Class A mission is like the space station, right? Not only is it a big, very expensive, complex system, but human lives are on the line. The James Webb Space Telescope, that's like $9 or $10 billion. That is a Class A mission. And you can kind of see going down like Mars missions, maybe Class B or C. GPS is like a Class B, so very high end, but not the top level. Like if any individual spacecraft breaks, no one's going to die. So that's why it's a B. And you kind of go down from there. So what was kind of interesting historically is that this worked and was good enough because we were building often one-of-a-kind space equipment. But you can see in the examples under Class D, I sort of put this variable in there. And what happened as space got more and more accessible, and especially as CubeSats and other small sats started getting used a lot more, we have this crazy variability in what we can do. At some of the top level, you might have like ISS payloads or other instruments on specific missions, maybe Class D, but still pretty high levels of mission assurance. And things start to, fall off from there. And that's not necessarily saying that they're not very capable missions, but the amount of time and effort we put into traditional Class A through D activities is significantly less, right? So you can imagine high school students are just kind of throwing together hardware and hopefully launching it. But you can imagine Marco that flew by Mars was built by JPL. They did a lot of things to make sure those things work, but they're still technically a Class D. So we have this huge variability, and no one's really been able to figure out how to describe and communicate that well. The other approach, right, how do you handle this, was essentially this newer idea, actually very new, called constraint-based mission assurance. And that was actually created partially out of lessons learned from this program, UNP. The idea is you have a resource-constrained mission, and we want to be able to move faster or cheaper as we evolve our systems. This is being used by parts of AFRL, other parts of the DoD a little bit, and the Aerospace Corporation. So it's only kind of, again, a pretty new idea. But the basic process here is you want to understand your scope of the mission and the things that are going to constrain you, whether it be cost or team or what have you. You go from there and you're constantly trading between what you can do, your scope, versus what resources you can apply to get there. So it recognizes that you're sort of in a weird bounding box. To get a little more specific for how these work, again, on the left side, Class A through D processes. This was taken from an aerospace report, kind of like the mission assurance guys. They break it up into three major categories and say, how do we execute the program? How do we sort of capture problems that may occur, overall oversight, capture things as they happen, and try to make improvements. And so underneath all of those, and they have 16 unique processes that they call out, and those all have details underneath them, right? So it's a pretty well-defined, structured system that has been developed over 30 plus years, right? So there's a ton of good knowledge base and input here. Constraint-based, on the other hand, is much more of kind of an agile type flow. where again, you understand what you're trying to do, your objectives, understand what pushes you and constrains how much you can get done. And the idea here is you quickly iterate, build, get feedback on what you're doing, and then start to assess how far can I go given what I want to do and what my resources look like. And then you essentially execute the highest value efforts first, and you keep iterating and improving until either you run out of money or time or something breaks. And if something breaks, then you may need to have a larger programmatic evaluation for your system, and you may redefine your objectives. As we just went through the system concept review, you kind of did an element of this loop, and some of the review came through the UNP office, but like this is sort of a flow that we do. You can imagine the big premise here is we actually use a lot of class A through D processes, whether it be in UNP or otherwise in like the small SAT community. We take the idea of like, well, grab and build up the practices that have, if you will, the biggest bang for your buck, right, given your constraints, and apply them. Don't do everything. Just grab the things that are the highest impact and go forth. And so that's kind of the, again, the trade-off that we're doing here. These are the two major approaches. One is very much based in like small SAT kind of thinking, and the other has been much more of the large systems that we've developed in previous years. A little bit more of a compare and contrast here. So class A through D works very well. Obviously, there's significant practices. It can be very rigorous, right? People have built systems that have lasted literally decades, have performed all their mission objectives and beyond. You can think like Cassini that went to Saturn. I think it was supposed to be up there for 5 years, and it was there for like 17. The Mars exploration rovers, they had like a 90-day lifetime. What did it last? 12, I think, maybe more. So 12 years, I mean. Some of these practices are very rigorous, and it's pretty well understood. Clearly, it doesn't really fit for things like constellations, non-unique spacecraft, as well as these kind of new subclass D crafter, new space type things. It's too heavy-handed for most cost and time limits. The constraint-based side, it does well at conveying the trade space between what technically and programmatic we can do, but it is generally more informal. Even if we do use some elements of class A through D, it's not all of a class description. But since it's new, it's not super well understood, and we're still developing a lot of it, right? It's not a real full mission assurance architecture. It's just a way to approach the problem. It requires a lot of experience to actually do this correctly. Experience which you and UNP will be getting, which is kind of cool. I'm going to pause there. Are there any significant questions or anything about kind of like these two approaches? Cool. You can leave messages in the chat too if any questions pop up in your head. I'm trying to give you guys a background on, if you want to go research this a little bit more and get into it, you absolutely can. So just trying to give you the overview of what exists. Let's take this and break it apart for how do you actually apply to things you can do on your program. And I think there are 6 major bins identified here that all of you guys can and probably should do. Not necessarily in any particular order, but test really does matter. Test is probably the top one in the end. And so testing, right? The hardware doesn't lie is a statement and saying we have around here, right? Is the hardware is your truth. It's not the analysis. It's not what you hope and have designed for. It is in fact reality. Testing really helps you assure that your mission is going to occur in a way that you think it should. Obviously, flat satting as early as possible, developing your software, seeing it actually running either in a simulated environment or on hardware, all those things are really important. Analyses obviously are a key thing, and that's a lot of why you go to school is learn how to do that. And the whole point behind this is understand if the problems you have need further studying and refinement, right? The whole real outcome of an analysis usually should be is what's hard? Do I need to work harder to make this function, or is my design good enough and I can kind of stop? A lot of the things that we do here, right? There's different types of models, your orbital models, computer-aided design stuff, right? Like SolidWorks, simulations, like how much time do I have to downlink every day? All those types of things are good analyses to help like bound your system. And depending on what those things tell you, you may end up doing more design and testing to either verify that your designs are correct, or maybe validate a larger model that you're trying to then inform given your actual mission. Other things that you can do, add margin. This is sort of just a practical application, is if you can make something designed, if you can somewhat over design a thing, sometimes that allows you to get away with not worrying as much about having the perfect performance, just because you have a lot of capability to take variability in performance. This can be very hard to do on a small sat, but sometimes it's not a big deal, right? So that's kind of when drivers come in. If you don't generate a lot of data, but you happen to have a radio that has a decent amount of downlink data rate, right? You don't need to do a whole lot of extra analysis. You can just say, look, I got tons of margin on my data rate, I'm good. So those types of things, wherever you can take advantage, is always a good way to sort of plan your system. Other things that we're going to talk about more and more in your upcoming reviews is this idea of off ramps. The idea here is defining alternate ways to solve your problem, right? And this may be just different approaches. It may be performance reductions, but that might save you time or money in the long run. So there's a variety of ways to do this, but it's sort of identifying like, I could build my system with an X-band radio or a UHF. UHF, I might not be able to get all my data down, but it's a much simpler system, right? So that's like kind of an off-ramp type trade that you guys would be looking at. And the key idea down below is if you don't have to solve a problem, but instead you can work around it, right? Don't solve a hard problem if there's just a better way to not even encounter that problem in the first place. That's the idea of an off-ramp. Obviously, reviews, we do a bunch with you guys. And this one is really about getting input and insight into the problems as well as the solutions, and making sure everyone, who may have expertise kind of can just give an input and check on whether or not something looks feasible. It's also really useful, obviously, for demonstrating progress, sort of conveying this idea that I understand my system enough to keep progressing. And that's a lot of what the UMP competition is trying to do with their reviews, is understand, can you progress forward? Requirements and your verification matrix, right? This sort of helps you define levels of how deep into a requirement you really need to show is good enough, right? So your verification methods allow you to sort of do a variety of potentially these things, especially test analysis, having margin, those types of things, to just say, yep, my system's capable, or nope, I'm not good enough yet, as shown by whatever verification method. And we'll talk about this more, but if you look in, say, the UMP user guide, we have that big test matrix, and we talk about the 5 tests. And it's just sort of like, how do you approach solving your problems? So the other example I have here is, do you use a 1 node thermal model or a 100 million node model? What is sufficient to get things done? Mission assurance includes, but it's not necessarily adding things like redundancy, high reliability, doing really detailed analyses. You can do all that stuff for mission assurance, and you've probably heard of them or may hear of them in the future, but it doesn't have to be those types of things, right? It can be much simpler, as we call out here in these 6 types of activities. So you guys have been already doing, and will be doing a lot more of all of this. So that's kind of how we apply mission assurance to UMP. So moving on here, one of the other big topic areas that matters is this idea of risk management. So I want to open it up again, see if we get any comments or input. But how would you guys describe what risk management is?
I would say that risk management is sort of the path that you take to identify risks and then determine how they can be controlled. So for the management, it's specifically the things you do to reduce the risk or control it to an acceptable level.
Yeah, that's pretty awesome. Anybody else want to throw in their 2 cents? But that's a good definition. Oh, just got another one. Vincent again, understanding mission risks and how to reduce them. Yep. All right, cool. So this is probably a little bit more tractable of an area, but wanted to just describe it a little bit, give maybe a little bit of guidance on how you might approach it. Okay, so risk management, and I'm using these bubbles because I'll use them again in another slide or so, but the process to identify, capture and track, classify, and then handle a risk. And I'm defining risk here as essentially anything that affects your schedule, your cost, or your scope. Again, the purpose of doing this is understanding and conveying what might be an issue for you in the future and how, or if you even want to mitigate that problem, right? That's essentially risk management. And I wanted to also throw this bullet in here. This is important. I had a project manager when I was in school. He was a professional, but he threw this out. He's like, be careful about paranoia, right? It is very easy. I've done this as a student. I've done this as a professional, to list out all the things that you might be worried about. And that's not necessarily risks. I mean, they're kind of risks, but you're getting more into this idea of paranoia, right? Where you're like, I'm worried about extreme scenarios or things that multiple failures have to occur before I get to some other risk or super low probability occurrences. Like the risk of my spacecraft might die is not really a risk. Like that's just a thing that's going to happen. All spacecraft eventually die. So there's no real need to like capture and track that. It's more like, will it die too soon? Do I need to somehow keep it alive for longer? That's maybe more of a risk. But either way, just keep that in mind. Risks, schedule, cost, scope, be wary of paranoia. And generally in UNP, what we're looking for is for teams to perform risk management and mitigate risks as best as possible. That's not necessarily mitigating all risks all the time. The program management office and your teams will essentially kind of discuss and we'll actually trade between your timelines, money, and objectives to get to a system that you can actually implement. And that's a lot of the risk management that we'll be doing. We might not even call it risk management in conversations with you guys, but in the end, that's a lot of what happens, especially more towards the end or even in phase B after the 2-year cycle. So how do we do more risk management? So again, identify, capture and track, classify, and handle it. Okay, so this is the basic steps, and this is just something to kind of give you guys like a key for how would I go about doing this, and maybe even communicating to your teams how they should approach this as well. So in the identification box, right, the real question is does some part, a system, a specific failure mode, something like that pose a risk that you care about? A big important piece of this is any team member should generally feel enabled to identify a risk and bring it up to their team lead, the system engineer, the program manager, whoever on your team, your PI. Anyone should feel like they can bring up something that they're concerned about. Effectively, at that point in time, then you capture that and start tracking it. So really the question then becomes is this a risk? And if it is, then I'm going to start watching it and seeing what happens. A simple Excel sheet is an easy way to do this. You can get more advanced, but like that's a nice way to go. One other pointer, generally, UMP program should have fewer than 15 significant risks, probably a lot fewer than that, but you know, it really is a short list. And the way we usually capture these is with risks, you sort of have an if-then statement. So if some event occurs, then I have some impact. And generally, you want to sort of try to relate those things, again, back to your scope, your objectives, some sort of reduction to those, like what's happening. Or do I take a lot more time, maybe miss launch, or do I cost way more than the dollars you have on hand, right? That's usually how risks are conveyed and related as far as to what they're impacting. Next, we classify what this type of risk is. This is essentially saying, what's the importance of my risk? The two common ways people talk about this is likelihood and severity, right? So how likely is it to occur? And if it did occur, how much would it cause a problem? And so I try to give some examples here, and you can certainly do it differently, right? But likelihood is it's definitely going to occur, it might occur, or it's improbable. Similarly, right, for severity, it's like, if this happens, my mission's over. Or if this happens, I lose an objective, but other objectives are okay, or something like that, right? So you can kind of have a variable scale for how much this impacts you. Again, this shouldn't be classifying, it should be handling, the last major one. How are you going to deal with this risk? And there are three kind of big ways we talk about it. Either you mitigate it, so that's actively reducing the risk, like applying time, and effort to fixing your problem. You can also do something called watch it. So maybe this is a risk, but something you're not going to encounter right away, or something you're not totally sure you want to deal with yet. And so that's something where it's like, cool, we're tracking it, but I'm not going to do anything today. And you can always do the other end is, look, I'm going to accept this risk. I know it's going to be a problem, but we're just going to let it occur. And that might be something that's low severity and maybe occurs every now and then. So something like, hey, we want to have 5 passes a day, but some days we can only get 4. Okay, you're probably just going to accept that. If it's something where it's like, look, it has low impact, but it happens all the time, maybe that's something you don't want to accept, and that's something you end up mitigating or whatever. So there's a variety of ways to, or a variety of reasons why you may select how you're going to handle your risk. But those are the 3 big words that we use to describe how you handle it. I wanted to throw this up just again, so you guys have references you can go back to here. So the traditional mission assurance approach is pretty darn well captured by that aerospace report, the TOR 2011. Take a look at it. It's long. They have kind of a good executive summary up front, but then they have pages of tables for what each practice means for each class type. I learned a lot from that document. It's pretty darn good. There's a few others, right? NASA kind of calls out how they define A through D, and the original classification definition is also out there in that DoD handbook. That's a old document. No one uses it actively today. There are a bunch of other aerospace reports as well. One I'm throwing out here is the Do No Harm for Launch. That has elements of mission assurance applied. But this is really good for you guys to understand, like, what launch vehicles and launch integrators to those vehicles care about. And so that might be a good just kind of background set of information for you to essentially make sure your spacecraft does not harm other spacecraft or the rocket. So again, there's a whole litany of other things that you could look for, but I think these are reasonably good references if you want to start digging. And then the constraint-based approach, again, is pretty new, but there's a variety of thinking and papers that have been written by us for how to do this. Aerospace, again, keeps popping up a lot. They have a good report from 2017 talking about, like, how do we improve overall mission success? Really, mission, that's a mission assurance question of CubeSats. And they have a nice table which effectively reflects many elements of the table I showed you guys back here. So it talks a decent amount of these different pieces. And then NASA also has kind of a handbook for how they think of, really Goddard, for what they think of how to do CubeSat missions. There are plenty of ways to dig into this, see how it applies to your missions. And obviously the UMP program office can also provide you guys input and insight as you need. Conclusions to this, especially if you talk to other industry advisors and other things like that, depends on who they are, but don't kill yourself with mission assurance. I think a lot of the things we ask for in the user guide and a lot of the program reviews that we have structured already have a lot of the key mission assurance activities built into them. So if you think you need to apply more or do things differently, that's a great conversation to have. But yeah, I don't think you have to go super out of your way for adding a bunch of stuff on any of your individual missions. But yeah, key points here: identify what's hard and what matters for your mission and put your focus there, right? Don't focus on little stuff or things that are kind of tangential. Understand what is important to getting your mission successful. Just because it hits everyone all the time. Software is always a stumbling block. And if you can get that right, you usually are going to have a lot more success everywhere else. Put your time there as much as you can. Risk management, yeah, you don't need to be overly burdensome with this. It really is supposed to be a tool of itself to essentially help you understand what problems do I have, convey those to others, and get people to help you understand and decide how to invest your time, right? And that goes back to figuring out what's hard and what matters for your mission. Generally, if you guys have questions or need further help on these things, right, that's why the PMO is here. So went pretty fast on that, but didn't want to belittle it too much. It's mostly, can get pretty dry. So yeah, just wanted to keep it fairly high level. Hopefully this was a good enough primer for everyone. So yeah, thank you.